Alright, what we're going to do in this video is we're going to continue with the numerical examples for hypothesis testing. The previous two lectures on hypothesis testing really introduced a lot of vocabulary, a lot of new concepts, and we also went through some examples for how to write the null and the alternative hypothesis, and we also went through one example about how to determine whether or not we're going to reject or not reject our null hypothesis. And that one example that we went through, we did both the methods that we've talked about so far, which were converting everything to the units of the problem or leaving everything in terms of z or t values. In the previous lecture, towards the end, we went over that one numerical example, and I went through that one really slowly because it was the first example that we went through. These next couple of examples that we're going to go through, I'm going to start to speed things up a little bit more. So therefore, if it's starting to go a little bit too fast for you, as always, you can pause the video, rewind the video, and listen to it again. If there are some concepts which you're still a little bit shaky with, I highly encourage you to go back to the last lecture video and look at that one example that we went over towards the end of that lecture video, because I tried to give lots and lots of details in that one. Alright, so let's start off with this example here. The mayor of a large city claims that the average net worth of families in the city is at least $300,000. A random sample of 100 families selected from the city produced a mean net worth of $288,000, with a standard deviation of $80,000. Using a 5% significance level, can you conclude that the mayor's claim is false? First, it's asking us to use method number 1 by converting everything to the units of this problem. Alright, so as I've done with all of the examples so far, first off, how do we know that this is a Chapter 8 question? Here it's asking us to test some claim, which is just another way of testing some hypothesis. So therefore, we know that we're doing hypothesis testing. And then the only chapter that we've done hypothesis testing so far is Chapter 8. Now, how do we start off our Chapter 8 questions? The first step in doing Chapter 8 questions is to write down our null and our alternative hypotheses. Again, what I'm going to also recommend that you do is, as we go through these questions, I'm going to recommend that you pause the lecture video, give them a chance by yourself, and then play the lecture video to see if you got these problems right. You can either do it at the beginning of the problem and work out the entire problem by yourself, or you can pause it before each step and do that step by yourself and then continue the lecture video. But don't just watch the lecture video, try to work along with what I'm doing up here. So for step number 1, for writing down the null and the alternative hypothesis, how do we write those down? We always start off with those 3 questions. And the first of those 3 questions is there a statement which contains equality? And if we read this here, the answer to that question is yes. Because the mayor of a large city claims that the average net worth of families in the city is at least $300,000. And what's the symbol that we have for at least? It's greater than or equals to. So since we have a statement which contains equality, that becomes our null hypothesis. So our null hypothesis is greater than or equals to $300,000. The second question that we ask ourselves whenever we're writing down our null and our alternative hypotheses is there a statement which does not contain equality? Well, we can think of that we've already used up all the information in this first sentence. The second sentence talks about our sample, so that's not talking about a population parameter. And here, in the last sentence, it's telling us what to do in order to test this claim. So the answer is that no, we do not have a statement which does not contain equality. So therefore, what does our alternative hypothesis become? It becomes a complement of our null hypothesis, so strictly less than $300,000. And lastly, the third question that we ask ourselves whenever we're writing our null or alternative hypotheses is, what's our parameter of interest? We're looking at the average net worth, so therefore mu is still our parameter of interest. We have yet to do an example where P, the population proportion, was our parameter of interest. But we'll get to that. That's step number 1. What's step number 2? Draw a picture. So regardless of whether or not we're going to be using our Z distribution, our standard normal distribution, or if we're going to use our student's T distribution, we're always going to have a bell-shaped and symmetric curve. What is this distribution going to be centered on? $300,000, which is our hypothesized value. And what's the symbol for the hypothesized value? Mu naught. The next thing that we want to figure out is how many rejection regions do we have and where are these rejection regions? So what do we use to determine where our rejection regions are? We use the alternative hypothesis. The alternative hypothesis tells us where our rejection regions are. And again, the quick and easy way of determining where our rejection regions are is if we can draw a horizontal line on this math symbol, then it's going to point in the direction to where our rejection region is. Here I drew a horizontal line. Now we have an arrow that points to the left. So therefore we have one rejection region on the left-hand side of our distribution. What's the value called that signifies the beginning of our rejection region? Here. That value is called the critical value. And what's the symbol that we use for the left-hand side critical value? Capital C. Alright, what else can we add to this graph up here? Well, we know that we have just one rejection region, and we put alpha into our rejection regions. So this time, we're going to clump all of alpha into this rejection region. We're no longer splitting alpha up into two rejection regions in this example. We only have one rejection region, so therefore we must put all of alpha into this rejection region. Now how big is alpha? 5%. Because alpha is synonymous with our significance level. So therefore alpha is equal to 5%, or written as a decimal place, it's 0.05. Right, and that's what we know so far for our diagram. What's step number 3? Step number 3 is the first step that we took in Chapter 7 questions whenever we were dealing with estimations of means. And that is n greater than or equal to 30, and is sigma known? So let's do it. Is n our sample size greater than or equal to 30? We have a random sample of 100 families, so therefore the answer to that question is yes, and that n is equal to 100. Do we know sigma? Again, sigma stands for the population standard deviation. And here, the standard deviation that we're given is in reference to the sample that we're taking, right? Here we have a random sample of 100 families. That sample has a mean of this and a standard deviation of this. So therefore, the standard deviation corresponds to that sample of 100 families. So therefore, no, we don't know sigma. We only know S, the sample standard deviation. So S is equals to $80,000. So what does this mean? We answered yes to the first question, but no to the second question. So therefore, here we're going to be using z values. Again, the only time that we use t values is if we answer no to both of those questions. But now here's something that's really important. It's z sub alpha, not z sub alpha divided by 2. Because we're not dividing alpha by 2 because we only have one rejection region. So therefore, we're looking for z sub alpha. Alright, well let's do it. This z sub alpha is the same thing as z for 0.05. And what's the z value that corresponds to 0.05? Well, we can either use the t table or the z table to determine that we're going to get 1.645. Again, remember that I'm always going to talk about these z values as being positive values. Keep in mind here that this critical value is on the left-hand side of our distribution. So if we want to look at this critical value, technically speaking, it's negative 1.645. But the way that I'm going to teach you is, for the formulas that we use, I'm going to consider these z sub alphas, or z sub alpha divided by 2's. I'm going to talk about them as if they were always positive values. So that's step number 3. What's step number 4? We're going to figure out what our critical value is in terms of the units of the problem. So here we have one critical value. It's our left-hand side critical value, which we're designating by C. And whenever we're trying to calculate out the left-hand side critical value, we take mu naught and we subtract z sub alpha now times s divided by the square root of n. Remember, go back to the last lecture video if you need to. But here we're going to use z values unless we answer no to both these questions, and here we use t values. And up here in the numerator we're going to use sigma if we know sigma, but whenever we don't know sigma we're going to use the sample standard deviation s instead. Here we don't know sigma, the population standard deviation, so we're going to use s. So let's plug values into this formula. What is mu naught? Mu naught is our hypothesized value. It's a value that we're going to center our distribution on, which is coming from our hypotheses. That's why both those values must always be the same in this course, because these are the types of problems that we do. So therefore here we're going to have $300,000 minus our z value is 1.645 times s, which we already said was $80,000, divided by the square root of n, and we said that little n was 100. So therefore, if we do this arithmetic, this is going to come out to $286,840. So therefore, here, this critical value, we can also say that this is $286,840. Now keep in mind this. If you said that this z value should be negative, and you plug in a negative z value into this formula, then you're going to be subtracting a negative z value, or adding it, which means that you're going to have $300,000 plus what's to the right of here. But $300,000 plus an amount is going to be above $300,000. So therefore you're going to come up with a value that's above this or to the right of this, and that would simply be incorrect. So therefore, that's why I keep emphasizing, I keep repeating myself, that I'm going to consider these values right here, these z values, to always be positive values, so that if you need to find just the left-hand side critical value, you know that you're going to take mu sub naught and subtract something from it, hence this symbol. And if you try to find out the right-hand side critical value, you can take mu naught and add something to it, which would then give you a plus symbol right here. So you can imagine that if you're trying to find the left-hand side critical value, the left-hand side critical value is below the mean, so therefore you're always going to be subtracting. And if you try to find the right-hand side critical value, it's above the mean, so you can always add that value. That's the way that I teach it. Sure, there's different ways of doing it and different ways of teaching it, but this is what I found to usually work out best. Alright, let's go on to step number 5. What's step number 5? Step number 5 is to figure out what our test statistic is. Since here we're dealing with the means, our test statistic is our sample mean, x bar, and x bar is equals to 288,000 because that's what's given to us in the problem. That the mean of our sample is equal to 288,000. So therefore, this right here is a test statistic. Then in step number 6, we try to see where our test statistic falls. Our test statistic is x bar, which is 288,000. Our critical value is $286,840. So therefore, 288,000 falls somewhere like right here. Somewhere above 286,840, but below 300,000. So you can think of this as being $288,000. So therefore, our test statistic is not within the rejection region. So therefore, we're going to say that since x bar, which is $288,000, is strictly greater than $286,840, which is our left-hand side critical value, we do not reject the null hypothesis that mu is greater than or equal to $300,000. All right. Now let me say something about this because sometimes I get some questions about this example. And that's this. This mayor is saying that the average net worth is $300,000. But we found out in our sample that it's just really $288,000. So we're below what the mayor is saying. Why are we not rejecting that mayor's hypothesis? And the answer is this. We are giving the mayor a certain amount of wiggle room. Right? Remember, that's how I defined the margin of error in Chapter 7. I said, let's give our estimate a certain amount of wiggle room. Here what we're saying is, all right, mayor, I'll give you wiggle room all the way down to $286,840. But if we come up with a sample average that's below $286,840, we're going to say that your claim is wrong. But as long as you're above $286,840, we'll say that you fall at least into our wiggle room. And that's what happened. We took a sample. The sample said that, yep, even though it was a little bit less than $300,000, it still fell within that wiggle room that we was providing the mayor. Right? Think about it like this. If the mayor says the average net worth is $300,000, and you take a sample, and the sample comes out to be $299,999, so just $1 below what the mayor claimed, you're going to call the mayor a big fat liar? Probably not, right? It's like $1 off. If you found out that it was $299,998, $2 below, again, would you call the mayor a big fat liar? Probably not. So how low are you going to go until you tell the mayor, all right, this low and no further? Well, at a 5% significance level, or a 95% confidence level, you're going to say that the lowest you're going to go is $286,840. And that's why, even though our sample average is below $300,000, it's still above our critical value. All right. So let's go on to method number 2. Now, what does method number 2 do? Method number 2 leaves everything in terms of z values or t values. So if we employ method number 2, what is different about step number 1? Nothing. The way that we write our null and alternative hypothesis has always been the same and will always be the same. I'm not changing anything about that. Step number 2. What's different about step number 2? For method number 2. Nothing. The diagram that we're drawing is supposed to help us get a visual grasp of what we're trying to do. So therefore, our picture still stays the exact same thing. It's just trying to get a grasp on stuff. What about step number 3? What changes about step number 3? Nothing. Step number 3, we're again just trying to determine whether or not we're using z values or t values. So we still go through that same process whenever we're dealing with the means. So therefore, step number 3 stays the same as well. What about step number 4? What changes about step number 4? Well, in step number 4 for method number 1, we converted everything to units of the problem. Here the units of the problem were dollars, but we don't want to convert stuff to the units of the problem. Here we want to leave everything in terms of z or t values. So therefore, we're going to say that the left-hand side critical value is just going to be a z value. And we already determined that the z value was negative 1.645. Now here it's important to keep it at negative 1.645 because our critical value is on the left-hand side of our distribution. All right, let's go on to step number 5. What changes about step number 5? Well, in step number 5, above, we looked at our test statistic, and our test statistic was X bar, and that was in dollars. We just left it at that because we were trying to leave stuff in terms of dollars. But now we don't want to have stuff in terms of dollars. We want to convert this to a z value. So therefore, we're going to say that our z value is equal to what? So let's think about this here. We have a sample size greater than 30, but we don't know sigma in this problem. That's what we answered up here above. So again, if we have a sample size that's large, but we don't know sigma, we're going to be using this formula right here. Showing you guys again where we're getting that in the notes. So I'm going to copy down this formula right here, which is z is equal to x bar minus mu sub naught divided by s divided by the square root of n. We've already said that x bar is our hypothesized value, which is $300,000. Oh, I'm sorry. X bar is our sample average, which is $288,000. Mu naught is our hypothesized value, which is $300,000. And we've already said that S, our sample standard deviation, is $80,000, and our sample size, little n, is equal to 100. If you do this arithmetic, we get a z value of negative 1.5, and this now is our standardized test statistic. Now, what do we compare this standardized test statistic to? Our z value for our critical value. So let's do that. We have a standardized test statistic of negative 1.5. Here, our rejection region begins at the critical value of negative 1.645, which again means that the test statistic, the standardized test statistic, does not fall within the rejection region. So therefore, just like we had above, for step number 6, we're going to say that since our standardized test statistic z is equal to negative 1.5, which is strictly greater than negative 1.645, which is our left-hand side critical value. Oops, just C, not C prime. We do not reject the null hypothesis that mu is greater than or equal to $300,000. So again, it doesn't matter which method we use. Method number 1 by converting everything to the units of the problem, or method number 2 by converting everything to z or t values. We should always arrive at the exact same conclusion, because basically all that we're doing is we're just changing the units, right? It's like changing 3 feet to 36 inches. Nothing changes about the distance. It's just a different unit. That's exactly what we're doing with method number 1 and method number 2. All right, let's go on to the next example. I'm hoping that that jogged your memory about what we did in the last lecture video. And what I'm going to recommend, and now highly recommend to you, is pause this problem, the lecture video for this problem. Do this problem by yourself for method number 1. Time yourself, because you should be getting quicker at doing these problems. Again, like I said at the end of the last lecture video, you should be able to do these problems in somewhere right around 4 minutes or so. Alright. So let's do it. PepsiCo contends that the average bottle which it produces in the Carolinas contains exactly 20 fluid ounces. A random sample of 25 bottles are selected with an average content of 19.9 fluid ounces and a standard deviation of 0.3 fluid ounces. Using a 95% confidence level, can you conclude that Pepsi's claim is false? For method number 1, we're converting everything to the units of the problem. We know that this is a chapter 8 question because we're trying to see whether or not we can conclude that a claim is false. So therefore, the way that we start off chapter 8 questions is by writing down our null and our alternative hypotheses. Whenever we write down our null and alternative hypotheses, we start off with the 3 questions. The first of which is there a statement which contains equality? So here, do we have such a statement? And we do. In the first sentence it says that PepsiCo claims that each bottle contains exactly 20 fluid ounces. So that's equals to, and because we have equality, it becomes our null hypothesis. So therefore, this is going to become equals to 20 fluid ounces. The second question that we ask ourselves is there a statement which does not contain equality? And the answer to that question is no. Because this next sentence, we already used up the first sentence, this next sentence talks about a sample, and the last one just tells us what we should be doing. So therefore, we do not have a statement which does not contain equality. So therefore, our alternative hypothesis becomes the complement of the null hypothesis, or not equals to 20 fluid ounces. The last question that we ask ourselves is, what is our parameter of interest? And here we're dealing with the average content of these bottles. So again, here we're using mu. The second step that we do for Chapter 8 questions is to draw ourselves a picture. We're using bell-shaped and symmetric distributions, regardless if we're using z-values or t-values. And this distribution is centered on our hypothesized value, which is 20 fluid ounces. And the symbol that we use for that is mu naught. We also want to determine where and how many rejection regions that we have. And we determine where and how many rejection regions that we have based off of our alternative hypothesis. Again, if we can draw a horizontal line that changes the symbol of our alternative hypothesis to an arrow, then that arrow is going to point to where our rejection region is. Here, it wouldn't change it to an arrow that either points only towards the left or to the right. So that means that we have a rejection region on the left and on the right. The value that corresponds to the beginning of our rejection region is called the critical value. The symbol that we're going to use for the left-hand side critical value is C, and the one for the right-hand side of critical value is going to be C prime. Since we have two rejection regions, we're going to split alpha up evenly into these two rejection regions because we have a symmetric distribution. And because we have a confidence level of 95%, we know that alpha is equal to 5%, and therefore alpha divided by 2 is equal to 2.5%, or 0.025. Now, for step number 3, which is similar to the first step that we did in Chapter 7 for estimation problems, since here we're looking at the means, right? Here we have mu's, not proportions. We're going to ask ourselves the two questions: is n greater than or equal to 30, and is sigma known? Here we have that the sample size, we only have 25 bottles. So here we're going to answer no to this first question, that n is equal to 25. And here it tells us that these 25 bottles have an average content of this and a standard deviation of this. So therefore we don't know sigma, we only know the sample standard deviation S. So we're going to answer no to this question, and this is going to become S is equal to 0.3 fluid ounces. So we answered no to the first question, we answered no to the second question. So therefore the symbol that we're going to use here is T. And since we have two rejection regions, this is going to become T sub alpha divided by 2. Whenever we're trying to determine T values, we don't just need to know what our alpha divided by 2 is, but we also need to know how many degrees of freedom that we have. So I'm going to write this subscript as T sub alpha divided by 2 with a certain number of degrees of freedom. So we already know what alpha divided by 2 is. Let's figure out what our degrees of freedom are. And so far what we've been using for degrees of freedom is, I told you could remember that it's simply just our sample size minus 1, or little n minus 1. Again, we're going to change that in a future chapter, but for now you can remember it simply just as little n minus 1. We said that little n, our sample size, was 25, so therefore 25 minus 1 is equal to 24. So therefore, we're looking for a t value that has an alpha divided by 2 of 0.025 with 24 degrees of freedom. We can go to our t table, come over to the column that has 0.025 as its subscript, come down to 24 degrees of freedom, and we get the value of 2.064. Again, looking up these values was something that we completed in a previous chapter, in Chapter 7. So if that was a little bit shaky for you, please go back and review Chapter 7's lecture videos. The t-value that we looked up is 2.064. Again, remember that I'm considering these things to be positive values, even though our right-hand side critical value is 2.064, but our left-hand side critical value is negative 2.064, if we have them in terms of t-values. Step number 4 is to convert our left-hand side critical value and our right-hand side critical value, C and C prime, in terms of units of the problem. So therefore, we're going to have mu naught minus T sub alpha divided by 2 with a certain number of degrees of freedom times S divided by the square root of n. And for our right-hand side critical value, C prime, we're going to have mu naught plus T sub alpha divided by 2 with a certain number of degrees of freedom times S divided by the square root of n. We can plug values in now because we know that our mu naught is our hypothesized value, which is 20 fluid ounces. We already looked up our t value, which was 2.064. Our sample standard deviation is 0.3, and our sample size, little n, is equal to 25. Plugging in those exact same values into the formula for our right-hand side critical value, we get this. And doing the arithmetic on both of these, we get that our left-hand side critical value comes out to 19.88 fluid ounces. And our right-hand side critical value comes out to 20.12 fluid ounces. So therefore, if we convert these critical values to the units of the problem, this one over here is 19.88 fluid ounces, and this one over here is 20.12 fluid ounces. In step number 5 for method number 1, we look at our test statistic. Since we're dealing with the means, the statistic that we're interested in is x bar, our sample mean. The problem tells us that our sample mean is equal to 19.9 fluid ounces. And again, this is our test statistic. And now we're going to see whether or not our test statistic falls within our rejection regions or not. Well, 19.9 fluid ounces is ever so slightly above 19.88 fluid ounces. So therefore, we are not in the rejection region. We're literally just above the right-hand side critical value, the left-hand side critical value, but below the right-hand side critical value. So therefore, in step number 6, what we want to say is that 19.9, which is our test statistic, I'll say that this is x bar to give myself a little bit extra room, which is x bar. 19.9 is strictly less than 20.12, which is the right-hand side critical value, but strictly greater than 19.88, which is our left-hand side critical value. And since this is the case, we do not reject the null hypothesis that mu is equal to 20 fluid ounces. That's using method number 1. In method number 2 now, again, I highly recommend that you pause this lecture video and try this by yourself. Here, for step number 1 in method number 2, where we're converting everything either to z values or to t values, here we're converting stuff to t values since we answered no to both of these questions above. But nevertheless, when we're writing down our null and our alternative hypothesis, that still stays the same. Step number 2, when we're trying to draw ourselves a diagram to visually see what we're trying to accomplish, step number 2 also stays the same. In step number 3 for method number 2, when we're trying to determine if we're using z or t values by answering these two questions, that also stays the same. Now let me pause here for a second and say this. I'm saying that these three things are staying the same. If we ever start off with method number 2 first, you shouldn't just be writing down same. If we start off with method number 2 first, you should be going through these steps that we did up here. And if you do method number 1 after that, then for method number 1, you can write down same. Right? Now, also, on your homework or the exams or the final exam, it's going to tell you which method to use. You don't always have to go through both of these methods. Sometimes they'll tell you explicitly what method you should use, and sometimes the answer choices that you have are going to dictate which method you should use. If your answer choices are in terms of the units of the problem, well, you should be using method number 1. If your answer choices are in terms of z values, well, you should be using method number 2. If it's some free response question like on the final exam, like you might see on the final exam, then they'll be explicit about which method that they want you to use. And if they're not telling you which method that you should use, you can use any method that you want. Alright, so let's continue with this problem. Now in method number 2, for step number 4, we're going to figure out what our critical values are. But now we can have them in terms of t values, which is what we already looked up before. We already said that our critical values in terms of t values were either negative 2.064 or positive 2.064. So for step number 5 then, we want to figure out our standardized test statistic. Oh gosh. Statistic. Whew, that was hard. Standardized test statistic. And now, again, looking at the notes from before, whenever we have a small sample and sigma's unknown, like we have in this problem, our standardized test statistic is a t-value. And the formula that we're going to use to calculate out the standardized test statistic is this formula right here. So therefore, our standardized test statistic is now a t is equals to x bar minus mu sub naught over s divided by the square root of n. And if we plug values in here for x bar, we already said above that this was equal to 19.9 minus our hypothesized value of 20 divided by our sample standard deviation of 0.3 divided by our sample square root of our sample size, which is 25. If you do this arithmetic, we get that our standardized test statistic is equal to negative 1.67. Now what we're going to do is we're going to compare this standardized test statistic to our critical values. And here you can see that negative 1.67 is definitely above negative 2.064 and below 2.064. So again, you can think of this right here as being negative 1.67 in terms of a t-value. So now it becomes a little bit clear, right? Here we were saying that we were ever so slightly above this critical value. But now if you look at negative 1.67 and negative 2.064, we can actually see that it's quite a bit above this critical value. So what we're going to say then is that our t-value, which is our standardized test statistic, is negative 1.67. which is strictly less than 2.064, which is our right-hand side critical value, but strictly greater than negative 2.064, which is our left-hand side critical value. So this is step 6, and I'm going to say that since this is the case, we do not reject the null hypothesis that mu is equal to 20 fluid ounces. Again, we're either always rejecting or not rejecting our null hypothesis. The conclusion that we're forming is always in reference to our null hypothesis. We're not making these in reference to the alternative hypothesis. That's the first thing that I want to re-emphasize here again. The second thing that I want to mention is, I always say to reject or not reject our null hypothesis. Keep in mind that some people will say that you either reject or accept the null hypothesis. And technically speaking, that's okay. Your textbook, I believe, either uses reject or not reject the null hypothesis. So that's going to be the phrase that I'm going to stick to as well. But keep in mind that you might hear this as to reject or to accept the null hypothesis in other settings. Alright, let's go on to example number 4. And I'm really hoping that these problems are getting easier for you. The steps are getting easier for you. As you can see, there's a lot of steps in these problems. But I'm hoping that those steps are easier, even if there are quite a few of them. Alright. So, let's do this here. Question number 4. And again, I'm going to encourage you to pause this lecture video to give this one a shot by yourself. But we're going to try to do this one, at least one of these methods, in 4 minutes or less. So this is approximately the pace that you should be working at. And obviously, whenever you're working out these problems, especially if it's a multiple choice question or a series of multiple choice questions, you're not going to be writing down every single one of these steps. So before I get into example number 4, let me backtrack here. And let me show you, if these are multiple choice questions, what these multiple choice questions are typically going to be phrased as. Usually one of these questions, so one of these methods here, is going to be phrased either as 2 or 3 multiple choice questions, if it's on the multiple choice section of the exam. One of those multiple choice questions is usually step number 1, to write down the null and the alternative hypothesis. And like I said, you should be working at the pace of approximately 1.5 minutes per question, if it's a multiple choice question. So you should be able to write this down in no more than 90 seconds. What you should really be able to do is write this down in about 45 seconds or so, which should help you save a little bit of time that you can allocate on the next couple of portions. Because what the second question will ask you to do is it usually asks you to determine what your critical values are. And to get to the critical values, right, these two values right here, it's going to take you a little bit of time, but you should be able to get that in about 90 seconds or so. Or if you're saving some time up here, you can use it down here. Now, sometimes what they'll do is they'll break it up into 3 multiple choice questions, and they'll also ask you whether or not you're going to accept or reject the null hypothesis. So it's going to say, state your critical values, and then it's going to ask you to interpret whether or not you're going to accept or reject your null hypothesis. That's if it's broken down into 3 questions. So you should have about 4.5 minutes to do that. Now, sometimes what they do is they'll make this first one question number 1, but sometimes they'll combine these two into just one multiple choice question. So that multiple choice question will say something like, state your critical values and whether or not you accept or reject the null hypothesis. And then what you should be able to do is you should be able to do all of this right here in 90 seconds or less. Which means that now it becomes really, really, really important that you save some time when you're writing down your null and your alternative hypothesis. You shouldn't take a whole 90 seconds to do this. And some of the time that you're saving up here, you can use on these subsequent portions. Now, that's for the final exam. For my in-class exams, usually what I do is I try to have some easier questions spread out through the exam. And I'll mix in some of these types of questions where I break them up into 2 multiple choice questions, or where I just have these right here clumped as 1 multiple choice question. So that way you can save some time on the easier questions that are spread throughout the exam. But you still should make sure that you can working through this stuff here relatively quickly. Which, now going to this next example, that's why I'm saying that you should be able to work through one of these methods in 4 minutes or less. If you can work through one of these methods in 4 minutes or less, you should be good to go. So let's see if we can get through one of these methods in 4 minutes or less. Like I just got done saying, I'm going to be writing down everything that I'm saying. Chances are whenever you're doing this on an exam, you're not going to be writing down everything that you're saying. But I'm still going to try to do it in 4 minutes or less. Alright, so let's do it. The head of TSA for Chicago's O'Hare Airport claims that the average wait times to pass through security at this airport is no more than 15 minutes. Suppose that it is known that the standard deviation of wait times is at least 2 minutes. A random sample of 36 travelers are selected with an average wait time of 17 minutes. Using a 10% significance level, can he conclude that the head of TSA's claim is false? For method number 1, it's asking us to convert everything to the units of the problem. So therefore, for method number 1, as for all methods, we're going to start off with answering those 3 questions in order to write down our null and alternative hypothesis. And that is there a statement which contains equalities? And here, we do have a statement which contains equality. That is no more than 15 minutes. And no more than 15 minutes is less than or equal to 15 minutes. So that becomes our null hypothesis. Our second question that we ask ourselves is there a statement which does not contain equality? And the answer to that question is no. There is no statement which does not contain equality. Because here it says, just suppose that it's known that the standard deviation of wait times is this. We have a random sample here of this, and here it's telling us what to do. So therefore, the alternative hypothesis becomes the complement of the null hypothesis, or strictly greater than 15 minutes. Third question that we ask ourselves is, what's our parameter of interest? We're dealing with the average wait time, so therefore we're going to be using mu. Step number 2 is to draw ourselves a picture to visualize what we're trying to accomplish. We're always going to use a bell-shaped and symmetric distribution. Here it's centered on our hypothesized value, which is also given to us by the symbol of mu naught. We're going to determine where and how many rejection regions that we have. I'm apparently going back to puberty, and my voice keeps cracking here during this problem. But nevertheless, we're going to determine where and how many rejection regions that we have based off of our alternative hypothesis. If we can draw a horizontal line that's going to show us where our rejection region is, here it's an arrow that's pointing to the right, so we only have one rejection region. The part where our rejection region begins is given to us by the right-hand side critical value, which is designated by C'. Since we only have one rejection region, we're going to clump all of alpha into this rejection region. And alpha is given to us by 0.1, since the significance level is synonymous with alpha. So writing 10% as a decimal is given to us by 0.1. Now we can go on to step number 3, which is going to be to ask ourselves the two questions: is n greater than or equal to 30, and is sigma known? Here we have that we have 36 travelers, so our sample size is greater than or equal to 30, n is equal to 36, and we also know that the standard deviation of all wait times is 2 minutes, so therefore that refers to sigma, so sigma is equal to 2 minutes. Since we're answering yes to both of these questions, we're going to use z values, but again, it's going to be z sub alpha since we only have one rejection region. So this is also z sub 0.1, and we can use our t-table to find out that our z value for this should be 1.282. Again, I'm going to call this a positive value, but now that's a lot more reasonable because our critical value is above the mean. Now for step number 4, we're going to convert this right-hand side critical value to the units of the problem. So we're going to have mu plus, since we're above the mean, z sub alpha times sigma divided by the square root of n. Our hypothesized value is 15 minutes. We already said that our z value is 1.282, sigma is 2 minutes, and n is 36. If we do this arithmetic, we get that this comes out to 15.427. So, 15.427, for step number 5, then, we're going to compare, or we're going to find out that our test statistic is equal to x bar, which in our problem is telling us that the average wait times is 17 minutes. Therefore, if our critical value is 15.427 minutes, and our test statistic x bar is 17 minutes, that means that our test statistic is inside our rejection region. Which gets us to step number 6, and we're saying that x bar, which is equal to 17 minutes, is strictly greater than 15.427 minutes, which is our right-hand side critical value. And since this is the case, we reject the null hypothesis that mu is less than or equal to 15 minutes. Which should make sense because common sense tells us that wait times at Chicago's O'Hare International Airport is always more than 15 minutes. But using the numbers in this problem, this is the conclusion that we should come to as well. Alright, so that seems to have taken about 5 minutes or so. So obviously writing down all these individual steps right here is not something that you're going to do on a multiple choice problem. But I'm hoping that just for completeness sake, that helps you go through this problem too. Alright, going down to method number 2. We know that step number 1 for method number 2 is going to be the same thing. Step number 2 is going to be the same thing. And also for step number 3, we're going to have the same thing. But method number 2 starts to diverge from method number 1 once we get to step 4. Because step 4 above in method number 1, we're converting stuff to the units of the problem, which is minutes. But in method number 2, we want to leave things in terms of z or t values, which here we're dealing with z values. So therefore, we're going to just say that our right-hand side critical value is going to be 1.282. In step number 5, now we're going to try to figure out what is our standardized test statistic. And our standardized test statistic here, since we know that we have a large sample size and we know that sigma is known, we're going to have that this is x bar minus mu sub naught divided by sigma divided by the square root of n. If we plug values here, x bar was 17 minutes. Our hypothesized value is 15 minutes. Sigma is 2 minutes. And our sample size was 36. If you do this arithmetic, our standardized test statistic comes out to 6. We have a z value of 6. Which, if we have a z value of 6, and we have a right-hand side critical value of 1.282, so where our rejection region begins has a z value of 1.282, that shows that our standardized test statistic is way inside our rejection region. And again, the reason why I'm pointing this out is you might say, well, 17 minutes to 15.4 minutes is just off by, about a minute and a half, 90 seconds. You might say that 90 seconds in terms of wait times is just a small amount. But when you compare a z value of 6 to a z value of 1.2, now we're clearly super far off. So therefore, we're way inside the rejection region. And that's something that we're going to use a lot with the next method that we're going to learn, method number 3 that we haven't talked about yet, just to show how strongly we can reject or not reject the null hypothesis. So here, we're going to say in step number 6, we're going to say that since C prime, which is 1.282, is strictly less than 6, which is our standardized test statistic, we reject the null hypothesis that mu is less than or equal to 15 minutes. Alright, so we're starting to obviously go through these problems more quickly. If some of this stuff was going a little bit too quickly for you, feel free to pause the video, rewind the video, listen to stuff again. If after you re-listen to stuff again, if it still is too quick for you, go back to some of the previous examples, especially the one that we did at the end of the previous lecture video, because I went through that one super slowly. I tried to articulate absolutely every step that I took thoroughly, but you should be able to get through these problems somewhere right around 4 minutes. So please continue to practice these, especially the homework problems that you're going to do, to make sure that you can get through these problems in approximately 4 minutes. And what I mean with the problems is just one of the methods. You don't have to work through both of the methods in less than 4 minutes. Just one of the methods in about 4 minutes. Other than that, we're going to stop here, because in the next section that we're going to get into, the next part of the lecture notes, section 8.3, that's going to start to talk about the next method that we're going to learn. But we'll do that in the next lecture video.